So let's get right into some two-column proofs. So a pretty good tactic for dealing with two-column proofs is to start off by listing all of your givens and then stating the thing you are trying to prove as an assertion. So that's pretty much how I'm going to start these problems, unless something leaps out with the givens, which in this case, nothing really comes to mind. Okay, the givens don't obviously combine. I'm not saying there's no way to combine them, it's just not immediately obvious, but I'm going to go ahead and state the two givens. And then for line 3, I'm simply going to assert exactly what we are trying to prove. P implies not W. But we don't really have a good reason for this. That's why it's an assertion. So an assertion is going to be followed immediately by an assumption. And in this problem, we're asked to do a direct proof. So we're going to make an assumption for a direct proof. If you have asserted a conditional statement, you can do a direct proof. And if you have asserted a conditional statement, and we have, P implies not W, for a direct proof, what you assume is the hypothesis. So the hypothesis of this statement is P. So that's what we're going to assume. Having assumed the hypothesis P, if we can make the conclusion not W show up, then we'll be done. So having introduced a new statement into the mix, we have assumed that P is true. We ask, how does that combine with what we have so far? And the only line we can't use is line 3 because we have not justified this assertion yet. So P doesn't really combine with the negation of Q and W in any reasonable way. The fundamental statements are just totally different. However, we do have P implies Q. So if we take line 3.1 and 1, we can combine them into line 3.2 with P and P implies Q. By applying the rule of modus ponens, we can get out Q. Now our new bit of information is Q, and that does combine with line 2. However, before we can combine line 3.2 with line 2, what we need to do first is, well, there's a couple things we could do, but I'm going to apply De Morgan's law. The negation of Q and W is not Q or not W. So this is De Morgan's law on line 2. Now what we have is we have Q combined with not Q or not W. So either not Q or not W, however, we do have Q. So if we combine line 3.2 and line 3.3 by eliminating this or, so through the rule of elimination, if either, if either not Q or not W, but we do have Q, so we don't have not Q, then what we must have had was not W. So if you do not have this one, but you have one or the other, then you do have not W. And so now, having started from the assumption of P, we have shown that not W must follow. So having assumed the hypothesis P, we have shown the conclusion not W. So we can go ahead and say that all of this has now justified this assertion. It's no longer an assertion, it's been proved. And having proved the statement that we were asked to show here, this problem is done. All right, so let's prove this directly. Again, we're going to go ahead and start with our givens, S or B. P implies not B, given. For line 3, I'm just going to go ahead and assert the statement we are trying to show. Having made an assertion, we immediately make an assumption, and again, we are asked to do a direct proof. So I'm going to assume the hypothesis of the conditional statement we just asserted, P. Then we ask, how does P combine with things that we already have? Well, if we combine 3.1 with 2, P with P implies not B, we can use modus ponens and get out not B. Then in line 3.3, S or B, but not B, therefore S. And again, that's elimination, 3.2 and 1. So having made the assumption P, we were able to get to S. And again, in line 3.1, for a direct proof, we are assuming the hypothesis of this conditional statement. The only thing we cannot refer to is line 3 because it hasn't been proven yet, and we didn't. Okay, we referred to the assumption 3.1, but that's fine. We didn't refer to line 3 itself. But having gotten from P to S, we have concluded the direct proof of the statement P implies S. It's no longer an assertion, it's now been proved, and that was all the problem asked us to do. Moving on. Okay, it looks like we got some more stuff to work with here. So P implies Q implies R for line 1. For line 2, P implies S implies U. For line 3, P and Q or S. And for line 4, not R, and these are all givens. Okay. Now we're asked to do a direct proof, but the statement U, the conclusion here, isn't a conditional statement. So the direct proof here isn't going to be one in the sense of assert a conditional statement, assume the hypothesis, derive the conclusion. Here the word direct just means directly construct the statement U. So just playing around with our givens and nothing else, we're going to get out the statement U. So notice that we have two conditional statements whose hypothesis is P. I'd like to apply modus ponens to these, but what I need to get out is a P. Thankfully, in line 3, we have P and Q or S. So in line 5, if we specialize line 3, we can extract P. We can also specialize line 3 to get out Q or S. Okay, so line 3 says P and Q or S, so we can get out the P and we can get out the Q or S for the same justification, specialization on line 3. Now that we have that P, we can do modus ponens with line 5 and 1, and we can also do modus ponens with line 5 and 2. So if we combine P with P implies Q implies R, that's going to give us Q implies R. And if we combine P with P implies S implies U, that's going to give us S implies U. Okay, so our new information that we just got out, Q implies R, S implies U. One thing that I find helpful to do is ask, do we have any statements that we haven't actually referred to yet that we're allowed to, some statements that aren't assertions? So we did use line 1. That doesn't mean we're never going to use it again, but we have used it at least once. We've used line 2, we've used line 3, and we did so twice, but we haven't used line 4. Line 4 has never been referred to. It's not an assertion, it was a given. So let's ask, can we use line 4 with anything? And we can. In line 7, Q implies R, we have the negation of the conclusion. And that suggests that for line 9, we're going to go ahead and combine line 4 and 7, but that's with modus tollens. So Q implies R, but we don't have R, therefore we don't have Q. Now our new information is the negation of Q. And that we can ask again, is there anything we haven't referred to? We've used lines 1, 2, 3, 4, 5, but we haven't used line 6. So Q or S combines with not Q through elimination. If we either have Q or S, but we don't have Q, well then we must have S. So that's elimination between lines 6 and 9. Our new information is now S. We have never referred to line 8, but with S and S implies U, that's a quick modus ponens between lines 8 and 10 to get out U. And that was what we were supposed to construct. We now have the desired conclusion U as a legitimate statement. We never actually had to make any assumptions at all. Another direct proof. All right, let's just start with our givens. 1, 2, 3. A implies B or C. P implies A. Negation C. Given, given, given. So what we could do is we could go right ahead and state P implies B as an assertion and just get right into our direct proof. But perhaps one thing we might do is ask, do our givens combine in any way? And we have P implies A. We also have A implies B or C. So a legitimate thing that we can do, even if we're not sure if it's useful, is we can do transitivity between these two conditional statements. And this, of course, is not the only way to do the problem, but if P implies A, the conclusion is A. A implies B or C, the hypothesis is A. So this hypothesis goes to A, which then goes to this conclusion. So transitively, we can conclude that P must imply B or C. Then maybe for line 5, having run out of ideas on what we can possibly do, we'll just go ahead and we'll assert P implies B, because that's what we're supposed to do. Assertions have to be followed by assumptions. We're doing a direct proof, so for line 5.1, we're going to assume the hypothesis, P. Now the only line we can't refer to is 5, because it is an assertion. We can't refer to it until it's been proved. Of course, it's exactly what we're supposed to do in this problem, P implies B, so once it's proved, the problem's done anyway. So our new information is P. The only thing I can't refer to is line 5, but I can refer to line 4. So if I use modus ponens on line 5.1 and 4, P gets fed into P implies B or C, and we get out B or C. Now our new information is B or C. But if I combine lines 3 and 5.2, we've got some elimination. We either have B or C, we don't have C, therefore we must have B. And we've gone right from P to B, so from this hypothesis to that conclusion. So we've gone ahead and completed the proof of our assertion. It's no longer an assertion, it's now been proved, and that was all we were asked to do. Okay, I'd point out that this use of transitivity is totally optional. It could have appeared inside here. It could have just been having made the assumption P, you use modus ponens to get out A, and then with A, you use modus ponens to get out B or C. That would also be totally fine. So there's no one correct way to do this. All right, next up, let's prove indirectly. So I'm going to go ahead and start off with the givens. P implies Q, negation of P and Q. Parentheses are important here. Given, given. All right, now let's just charge forward and say, okay. I'm just going to state the negation of P. I have no reason to know that that's true, so it's an assertion. Assertions are immediately followed by assumptions, but we're going to do an indirect proof. Okay. So an indirect proof, you take your assertion and you negate the entire thing. So on a very, very formal level, what we would do is we would negate the thing we just asserted. Okay, now typically I wouldn't go through with this step of double negation. Not P is just the same thing as P. And honestly, generally having asserted not P, an assumption for an indirect proof would have just gone straight to P. I just wanted to point out that we're taking our assertion and we're negating that whole statement. Okay. For my classes, double negation is not something that I typically require to be its own line, so not P could have just been directly stated as P. Okay, so P is our new information. Let's go ahead and use modus ponens. Well, if we're using modus ponens, I must be referring to a conditional statement. The only one out there is line 1, P implies Q. If we're doing modus ponens, we need to have the hypothesis P, and we do. So modus ponens has to refer to 1 and 3.1. With P being fed into P implies Q, we get out Q. Our new information is now Q. That can't combine with line 1. I mean, we got it out with line 1. So we must be combining it with line 2. But The Q is buried underneath this negation. So our first order of business is going to be, let's distribute that negation out through a use of De Morgan's law. Now, either not P or not Q, but we do have Q. That's the negation of this argument of the or. So if I don't have the thing on the right, we must have the thing on the left. And that's a nice use of elimination between lines 3.3 and 3.4. And now what do we have? Well, we've gotten out a not P, but we also have a P. So since we were doing an indirect proof, our goal is to construct a contradiction. We have a P, we have a not P. Okay, your mileage may vary with different instructors, but I do require students to make this nice and explicit. I'm going to take these two statements, I'm going to conjoin them. 3.2 is a legitimate statement, and 3.5 was a legitimate statement, so I can stick them together with an and. And now what we have is the conjunction of a statement and its negation. That is a flat-out contradiction. So we have a statement and its negation. That is always going to be false. So line 3.6 is a guaranteed contradiction. Now the indirect proof is complete. Having made an assumption, I have derived a contradiction. And the assumption we made was that our assertion was false. So assuming our assertion is false, we get something that is a flat-out contradiction. Therefore, our assertion is actually true. So we box all this off. And this is no longer asserted, it's proved. And the reason for this boxing off of the assumption and everything follows is that if there was more to prove, these lines would now no longer be legal to be referred to. So in all the problems we've done so far, the desired conclusion of the problem, we assert it, then we prove it, then we're done. But it's totally feasible for a problem to have multiple assertions within it, in which case the proof of one assertion, once that statement is proved, you can use that statement, but you can't use the lines you used to prove it anymore. Okay, so that's the reason for this boxing off. All right, so the large size of the table might be scaring you. I just happen to know I couldn't fit it into one column here. We'll see why. All right, so we're going to start off with lines 1, 2, 3. P and Q implies R. P implies R implies S, not Q or M. These are our three givens. And without thinking very much, I'm just going to go ahead and say line 4. Let's just go ahead and assert what we are trying to prove. Now this is a conditional statement, so we do have to follow it up with an assumption. And since we asserted a conditional statement, direct proof could be on the table, but we are specifically asked to do an indirect proof, so we're going to negate the whole thing we just asserted and see what happens. Well, with a negation of a conditional statement, we have a true hypothesis and a negated conclusion. Now that we have a conjunction, I'm just going to specialize it. With the negation of S and M, I really want to do a De Morgan's law on that, not S or not M. That's De Morgan's law on line 4.4. Okay, having sort of run through a chain of stuff that I did fairly automatically, state what you want to prove. We're doing an indirect proof, assume it's negation. Negation of conditional statement, hypothesis and negated conclusion. With an and, I specialize. With the negation of an and or an or, I applied De Morgan's law. So all of that was fairly much on autopilot. Now I can ask, okay, what should I do next? Well, what givens have we not referred to? We haven't referred to any of them. If I want to use this, it's a conditional statement, so naturally I want to think modus ponens, modus tollens. For modus ponens, I would need to have P and Q. We do not have that. For modus tollens, we would have to have not R. Don't have that either. So I don't have an obvious way to use line 1. To use line 2, it's a conditional statement. I would need to have its hypothesis, P implies R, don't have that anywhere. Or to apply modus tollens, negation of S. I almost have that, but not quite. Here we have an or. Okay, so I might think specialization. To use specialization on an or, you need to have the negation of one side. Do we have a not M? No. Do we have a Q? Yes. So specialization between lines 4.3 and 3 will give us M. Okay. Remember, the only line we cannot refer to is an unjustified assertion, so the line we can't use is 4, but we can use these givens and we can use any of these. All right, with M, what can we say? Well, look at line 4.5. That's just asking for another specialization. Between lines 4.5 and 4.6, either not S or not M, but you do have M. So this side failed, so you must have that one. So we conclude not S. And that was exactly something we were looking for this given. A not S will allow us to apply modus tollens. So if we're going to apply modus tollens between lines 4.7 and 2, we're going to get out the negation of P implies R. And now I go back on autopilot. So with a negated conditional statement, we're going to say that's the same thing as hypothesis and negated conclusion. Now that we have an and, we're just going to specialize. All right. So this is getting to be fairly long, but what I do want to point out is that a lot of this was done without thinking very much. We just did given, 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 assert the desired conclusion. We were told to do an indirect thing. Negated conditional statement, hypothesis and negated conclusion. We've got an and, specialize, specialize. I've got a negated and, De Morgan's. We did have to do a couple lines of thinking here, but now again, negated conditional statement, hypothesis and negated conclusion. We've got an and, specialize, specialize. So now we go back and we play the same game with our new information. Well, look, negated R was something that we were on the lookout for to use in line 1. So we're going to go ahead and we're going to say with modus tollens between lines 1 and 4.10, we're going to get it out in line 4.11, the negation of P and Q. Again, autopilot. Let's apply De Morgan's law. Okay, well, let's see. We've got not P or not Q, but we do have P. So since the left of this or failed, the right must be true. And that's elimination between 4.12 and 4.9. All right, remember we were doing an indirect proof. So from this assumption, we're trying to derive a contradiction, but we have a Q and we have a not Q. So let's conjoin them. This is lines 4.3 and 4.13, and that is an obvious contradiction because we have a statement and its negation. So from this assumption, we were able to get a contradiction. Therefore, the assumption must be wrong, but it was the negation of this assertion, so that assertion must be true. Proof complete. A direct proof here would be faster, but we were asked to do an indirect proof, and there it is. Okay, another indirect proof, but a shorter one. So, given, P implies Q, not P implies R. There's a way to do this without doing an indirect proof using one of the lesser known distributive properties, but let's not get into that. So for 3, let's just go ahead and state what we are trying to prove. It's an assertion, so it's got to be followed by an assumption. We were trying to do an indirect proof, so we are going to negate exactly what we asserted. And now at some point, we are working towards a contradiction. So some number of lines later, we're hoping to see some sort of contradiction. Here's the basic format of our proof. Without thinking at all, state the givens, assert what you are trying to do. It wasn't a conditional statement, so direct proof is off the table. So let's do an indirect proof, assume it's negation. Since we're doing an indirect proof, we're working towards some sort of contradiction. Without knowing anything at all, we've got the format of our proof down. But we do know some stuff, so for line 3.2, let's do a De Morgan's on what we just assumed. That's an and, so let's specialize it. Okay, we're looking for a contradiction. I don't see any contradictions yet, but we haven't used either of our givens. So P implies Q, not P implies R. And our new information is the negation of this conclusion, the negation of that conclusion. So two different applications of modus tollens between lines 1 and 3.3, or 2 and 3.4 respectively. So with P implies Q, not Q, modus tollens gives us not P. With not P implies R, but not R, modus tollens gives us not P. As I've mentioned, double negation I don't really require to be its own step. So P implies Q, not Q, therefore not P. Not P implies R, not R, therefore not P. And now we've got a contradiction staring us in the face. We have P, we also have not P. Let's just conjoin them. And that is our contradiction. So we have conjoined lines 3.5 and 3.6, and line 3.7 is an obvious contradiction. So from that assumption, we got a contradiction. Completing the indirect proof, the assertion is proved. Okay, finally for this set of exercises, let's just go ahead and not think very hard. We'll just throw down a given. We'll throw down a given. And heck, since we're on a roll, let's throw down a given. Next, without thinking, I'm just going to assert what we're trying to do. It's not a conditional statement, so assertions have to be followed by assumptions. Sorry, not assertion, assumption. Assertions have to be followed by assumptions. It's not a conditional statement, so direct is not an availability. So indirect, which means we're going to assume the negation of what we just asserted. We asserted not C, so its negation, C. Now we start playing the game. Well, with a C and a C implies P, we've got a nice modus ponens available. Between lines 1 and 4.1, C is going to get us P. But then we have another modus ponens available to us. Between lines 2 and 4.2, we get out Q or not C. Now, since we have Q or not C, but we have C, this side failed, so that side has to be true, and we get out a Q. So elimination gives us a Q between lines 4.3 and 4.1. If you spotted a different elimination, you might be correct, but this is the one I'm going with. Now we have Q, but earlier we also had not Q. So between lines 3 and 4.4, we're just going to do a conjunction, and that is a flat-out contradiction, Q and not Q. Line 4.5 cannot possibly hold. So from the assumption in line 4.1, we derived a contradiction. Completing the indirect proof, the assertion is justified, and the problem is done.